Good morning, students. I welcome you all for another lecture on digital circuits. Today, I'm going to discuss about a concept called registers. Coming to introduction part, a register is a sequential logic circuit. A register contains a group of flip-flops. Flip-flop is a single bit storage element. For increasing the number of bits stored in a register, we need increase the number of flip-flops in the register. For example, to store an n bits in an n bit register, it must have n flip-flops. Basically, registers are designed by using D flip-flops because D flip-flops are data flip-flops. We know that. What are the input we are giving to the input side of D flip-flop? That is simply transferred to output whenever the clock pulse comes to the D flip-flop. Basically, a register is a group of flip-flops. We know that a flip-flop is a 1-bit storage element. A register is a group of flip-flops, so that based on the number of flip-flops present in a register, the register can hold those many number of bits. If I extend this one to another statement, that is, a group of registers are called memory. So group of flip-flops is flip-flops, and a group of flip-flops is a register, and a group of registers are nothing but memory. Next, coming to different varieties of registers we have in that. The first one is a buffer register. A buffer register is a register, simply it can hold the data whatever we are giving to the input of the register is. Just now I told you that a register is nothing but a collection of flip-flops. This is a 4-bit buffer register. Here I have 4 D flip-flops, that is D flip-flop 1, D flip-flop 2, D flip-flop 3, D flip-flop 4. And the clock signal is commonly applied to all these D flip-flops, so that your register is a synchronous sequential logic circuit because all the flip-flops are taking common clock signal. Once we are applying this clock signal to all these D flip-flops simultaneously, what are the input those D flip-flops have, it simply accepted and those are sent to their output sides. That is, if you are applying clock pulse here, what are the value that should be present on these data lines? That is D1, D2, D3, D4. That is the data inputs of these D flip-flops. That is simply reaches to the outputs of D flip-flops, that is at a Q1, Q2, Q3, Q4. These are the outputs are readily available from this 4 flip-flops. These are 4 outputs we consider as the outputs of a register. The job of this buffer register is this register can hold the data temporarily. And next type of register is controlled buffer register. So here there is a control logic circuit was available, which consists of 2 AND gates with an OR gate. Again, it is a 4-bit controlled buffer register because here I have a 4 D flip-flops. And here there is a control input called a load and store. Based on the logic level present on this control input, either the data which was present at input side of these D flip-flops either copied into the register, that may be X1, X2, X3, X4 values, or the previous values are stored again into D flip-flops. Coming to friends, this load slash store bar signal is equal to 1. That means this value is equal to 1, so that gate 1, gate 2, gate 3, gate 4, one of the input of these AND gates is equal to 1. At the same time, this load slash store bar signal is equal to 1, so that the output of NOT gate is equal to 0. Then this was connected to gate 5, gate 6, gate 7, gate 8 as one of the input. So that once an AND gate of one of the input is equal to 0, irrespective of other input, they can produce output is equal to 0. So that directly we can say that the output of gate 5, 6, 7, and 8 AND gates should produce logic 0 at an output. Now gate 1 output is now out and out is it depends on the X inputs. Because one of these inputs of AND gate 1, 2, 3, 4 is equal to 1. According to AND logic, 1 dot x1 is equal to x1. So that the output of gate 1 here is x1. And similarly, output of gate 2 is x2. And output of gate 3 is x3. And output of gate 4 is x4. And now for an OR gates, for this OR gate, x1 plus 0, so output is x1. Here x2 plus 0, output is x2. And here x3 plus 0, output is x3. And here x4 plus 0, output is x4. If you are applying a clock pulse, those x values are reaches to the output. Like this, the data was loaded into this register. Once this control input load stash store bar is equal to 1. If you took a reverse case, that is load slash store bar is equal to 0, then this value is 0, so that one of the inputs of this AND gate 1, 2, 3, 4 is equal to 0, so that the outputs of gate 1, 2, 3, 4 is equal to 0. At the same time, the output of this NOT gate is equal to 1, which is applied to one of the inputs of gate 5, 6, 7, and then 8. Now the output of these gates depends on the second input. The second input for gate 5, 6, 7, and 8 are nothing but Q outputs of that corresponding flip-flop stage. So here Q value is 1, that 1 is reaches to output of gate 8 as an input on OR gate, and that is applied to the input of D flip-flop. Similarly, this output is reaches to here through this gate 7 and this on OR gate, and this output is reaches to D input through this gate 6 and an OR gate, and output of this D flip-flop Q value reaches to the input of D through this gate 5 and this OR gate. So once the clock signal is active, then the same values are retained by these 4 flip-flops so that we can do store functionality. And here the combination of these 2 AND gates and an OR gate we consider as a control logic circuitry. Based on this control logic circuit, this whole register, either it can do a load function or it can do a store function. Next, coming to another important one is we have a different types of registers are available based on how the data was stored or how the data was retrieved from the register. Such register basically we can call as a shift register. So that concept now we are going to discuss shift registers. A register is capable of shifting the binary information held in these cells, each and every cell. Let you can assume, friends, these are the flip-flops present in this register. So the binary information can be shifted to their neighboring cells based on the selected direction. That means either you can shift data from most significant side to least significant side, that is called shift right, or we can shift data from least significant side to most significant side. Like this is we are calling as shift left. That means in a register we can shift our data to either directions, either it is shifted to right side or it is shifted to left side. If a shift register supports the data shifting to right side, that shift register is called a shift right register. If a register supports shifting of data to left side, such shift register we are calling as shift left register. And basically these shift registers are 4 types. We have 4 different configurations in these shift registers. Those are SISO, SIPO, PISO, PIPO. SISO means serial in serial out shift register. SIPO means serial in parallel out shift register. PISO means parallel in serial out shift register. PIPO means parallel in parallel out shift register. That means how the data was stored into the register as well as how we are retrieving the data from the register. Based on this, we classify them, our shift registers, into these 4 categories. Now we are going to discuss these shift registers one after other. My first shift register is serial in serial out shift register. In shortcut, we are calling as SISO shift register. Here I consider a 4-bit shift right register this is. So here the data was entered in serially, that was entered the first flip-flop, that is D flip-flop 1. Here the input is SN. And for the next stages, the output of first flip-flop is given to the input of second flip-flop. And for third flip-flop, we are applying second flip-flop output. And for next one, we are applying the output of previous. Like this, we are applying only the input at first flip-flop, and we are collecting data from the output of last flip-flop. That means the data was serially entered into this register like this fashion. So here the data bits are shifts from left hand side to right hand side by applying of clock pulse. The important thing about this SISO register is, let them, you can assume friends, this is an n-bit SISO register. To write data into this n-bit SISO register, we need n clock cycles because internally we have n flip-flops. For this case, here we have a 4 flip-flops are present. It is a 4-bit SISO register. If I want to copy 4 bits of a data into this 4 flip-flops of this SISO register, I need 4 clock cycles. After writing of a last bit into this flip-flop, the first bit is readily available at SOut. To retrieve the data from this register, I should took the help of only 3 clock cycles because I didn't want to retrieve a data from this, because after loading a data, this first bit was readily available for me. Only to took a data from this 3 flip-flops, I need 3 clock cycles. It is applied to generalized case. That means here your SISO register is an n-bit register. To retrieve a data from this register, we need n-1 clock cycles are needed. Next shift register is serial in parallel out SIPO register. This is the structure of SIPO. The data was entered serially like this. So here the data input is applied to the first flip-flop. The output of first flip-flop is given to the second, and second flip-flop output is given to the input of third flip-flop, and the third flip-flop output is given to the input of fourth flip-flop. See here friends, in this particular shift register, I collect an output from each and every flip-flop simultaneously. So from this I don't get the output of flip-flop 1, which is called Q1, and from this I was getting the output of second flip-flop, which is Q2, and from this point I'd like to take a output of flip-flop 3, that is a Q3, and similarly from this last flip-flop I collect an output of this flip-flop. From this is called Q4. But the data was entered into the register was serial, but retrieving the data from the register was happened parallel. In order to write a data into this particular register, let it be, it is an n-bit SIPO register. Again, I need n clock cycles to write a data into the register. But to retrieve a data from the register, I didn't want any clock cycles, because after loading a data into these flip-flops by applying of a clock pulse, the data is readily available at output side of the flip-flops. I can straight away access that outputs without taking any clock pulse. So that here I written as, to retrieve a data from SIPO register, 0 clock cycles are needed. So that here the outputs are directly we are accessing from the register itself. And next, coming to the third variety is parallel in serial out shift register, PISO register. So here the data was loaded parallelly, here A input, B input, C input, D input. And serially we are retrieving a data from this. So generally the general representation of this parallel in serial out shift register is like this. Data was loaded parallelly like this and retrieving data from the register sequentially. So here we are using again a control logic circuit, what we are just now using for control buffer register, which consists of 2 and gets followed by an OR gate. The same logic here again I was used. By applying of a clock pulse, these inputs are directly accepted by your D flip-flops. So here A input was available, and here the D input was available, and here the C input was available, and here D input was available only when if this shift slash load bar signal is equal to 0. If it is 0, the output of NOT gate is 1, so that here the second input for gate 1, gate 2, gate 3 is equal to 1, 1. So that the output of gate 1 here is B, here is C, and here is D. At the same time, the condition of gate 4, gate 5, gate 6 is they are producing logic 0. Why? Because here the signal is equal to 0. One of the input for AND gate 4, AND gate 5, AND gate 6 is 0. Irrespective of other input, they are producing 0 at an output. So that whenever this shift slash load bar is equal to 0, this register parallelly loads the inputs A, B, C, D into this 4 flip-flops of your PISO shift register. Similarly, if I want to retrieve a data from it, the signal should be is equal to logic 1. If it is a logic 1, automatically what happens is output of NOT gate becomes 0, so that one of the inputs for gate 1, 2, and 3 is equal to 0, irrespective of other inputs, they are producing logic 0 at their outputs. Now, the output of this OR gate is out and out is depends on the second input. This second input was produced by gate 4, gate 5, gate 6. For these 3 gates, one input is logic 1 because here I consider that the shift slash load bar signal is equal to 1. And the second inputs for this gate 4, gate 5, gate 6 was gate 4 is the output of first flip-flop. For gate 5, it is output of second flip-flop. For gate 6, the output of gate 3, sorry, flip-flop 3. So these values are reaches to the input of an OR gate. So that one input of OR gate is equal to 0. The second input here we may get a QA, here you may get a QB, and here we may get a QC. 0 plus QC, the output of OR gate here is QC. QB plus 0, here the output of OR gate is a QB. Here QA plus 0, the output of OR gate here is QA. Now by applying of a clock pulse, these values are accepted by your flip-flops, and only one bit I was retrieving at the end of this whole register. That is, I retrieve a data from only this last flip-flop. So this I return as serial data output. So if you observe in this entire process, to write the data into this PISO register, I need only one clock cycle. Simultaneously, these flip-flops can accept all these ABCD inputs. That was happened for only one clock cycle is needed. But to retrieve a data from this, we need n-1 clock cycles because this bit is readily available for us. For accessing of this, we need not want any clock cycles. But to retrieve a data from this, I need 3 more clock cycles. If you are applied for generalized case, it is I need n-1 clock cycles. And coming to the last variety is parallel shift register. So here the data is loaded into a register is parallelly, and similarly retrieving the data from the register also happened serially. See here friends, it is a 4-bit PIPO register, 4D flip-flops. They are receiving clock signals simultaneously from common clock source. For first flip-flop input is D1, output is a Q1. For second flip-flop input is D2, output is Q2. For third flip-flop input is D3, output is Q3. For fourth flip-flop input is D4, output is Q4. Once we are applying the clock pulse, this D1 is reaches to here, D2 is reaches to here, D3 is reaches to here, D4 is reaches to here. That means to write the data into the register, only one clock cycle is needed. But to retrieve a data from this register, I didn't want any clock cycle because the data is readily available at Q1, Q2, Q3, Q4. These are the 4 different configurations used to load the data into the register as well as to retrieve data from the register. And the next one is bidirectional shift register. If a register is capable of shifting a data in only one direction, that we are calling as unidirectional shift register, which may be shift left register or it may be shift right register. If it is a shift left register, the data bits are moving from a least significant side to most significant side. If it is a right shift register, the data bits are moving from most significant side to least significant side. We have another variety of a shift register is a register that can shift the data into both the directions. It is capable of shifting data to either left side or right side. Such a register we are calling as bidirectional shift register. In what direction we are shifting our data in the register, that is depends on the control signal, mode control signal M. If that mode control signal M is equal to 0, the register shifts the data to left side. That means it will be act as left shift register or shift left register. If M is equal to 1, it shifts the data to the right side, so that the time that register we can call as right shift register or shift right register. So this is that structure is. Again, here I was using control logic circuit. Similar to previous two cases, that is parallel and serial or shift register, we use this type of structure, as well as control buffer register case also we are using this type of structure. Only the control signal is changes. And here these inputs are changes. If it is a shift right, so here data bits are moving from this end to this end. For that case, I was using gate 1, gate 2, gate 3, gate 4. So gate 1, I was applying the serial input data. At gate 2, the first flip-flop output. For gate 3, second flip-flop output. At gate 4, third flip-flop output. Like this, the data bits are shifted to right side. And similarly, then we are retrieving the data from this. Similarly, if you have shift left data from left side to right side, then it is act as the shift left register. So serial shift left data is applied here. It is at a gate 8, gate 7, gate 6, gate 5. These 4 gates are used for shifting of data to left side. For gate 8, I was applying serial input for shift left. Gate 7, the input is nothing but third flip-flop. The last flip-flop output is given as an input to this. For gate 6, third flip-flop output that is given as an input to this. For gate number 5, second flip-flop output is given to the input of this. And from this Q, we are taking an output. So like this, either we shift our data to left side or right side based on the control signal. If this mode control signal is equal to 0, see here it is equal to 0. That means gate 1, gate 3, gate 2, gate 5. These inputs are is equal to 0. Once it is 0, then this gate 1, 2, 3, 4 outputs are 0. Then automatically gate 8, gate 7, gate 6, gate 5 are active. Then the data bits are shifting from left hand side to right hand side. If this mode control signal is equal to 1, then automatically it is 1, gate 1, gate 2, gate 3, gate 4 are active. At the same time, gate 5, gate 6, gate 7, gate 8 are inactive, because here the output of NOT gate is connected to these gates as one of the input. So this is about bidirectional shift register. And last, coming to an important one is universal shift register. Universal shift register is a register which has both the shift right facility as well as shift left facility along with parallel load capabilities. That means this register can shift data to left side, or it can shift data to right side, or it may supports parallel load data operation. So the universal shift register is a combination design of bidirectional shift register and unidirectional shift register with the parallel load provision. So here I'll go and take selection signals S0 and S1. What a register operation is. If both are 0, 0, no change. That means I didn't do anything. Whatever the value I have previously present in a shift register, it can hold it. Sorry. It can hold it as it is. If it is 0, 1, shift right data. If it is 1, 0, shift left data. It is 1, 1, parallel in data. That is parallel loading. So coming to the structure of this can be implemented with the flip-flops along with a multiplexers. Here I consider 4 by 1 multiplexer because here I was doing 4 different tasks. Here this S1 and S0 is act as a selection lines for my 4 by 1 multiplexers. Based on the combination present on this, I'll go and select the inputs of this multiplexer, and that should be reaches to I, and it is applied to the input of D flip-flops. And all these flip-flops get a common clock signal. If I place 0, 0 over S1 and S0, what happens? 0th input was selects. What is 0th input for all these multiplexer? Here it is Q1. It is given to flip-flop F1 output. Here it is Q2, which is an output of this flip-flop 2. It is Q3, it is an output of flip-flop 3. Q4, it is an output of flip-flop 4. That means whatever the data right now we have at these flip-flops, the same thing was written by these flip-flops. If S1 and S0 both are 0. If it is 0, 1, shift right. That means the data bits are moving from right side. That is from most significant side to least significant. That's why here the first bit is right shift serial in data. And this data, Q1 data is applied to here. So second input, Q2 data is applied to here. Q3 data is applied here. So from this, we are take it off data. That is shift right case. If it is 1, 0, then we are selecting a second input. Here the task is shift left in, so that at a second input, I'll applying serial left in data. At a second case, here for this mux, the second input is nothing but a Q4. And for this mux, Q3 is applied. And for this mux, at second input, Q2 was applied. And from this Q1, we are taking a data from the register. Last case is if both are 1, 1, then we are selecting a third input of all 4 by 1 multiplexers. What that third input was? Here it is I0, and here it is I1, here it is I3, and here it is I2, and here it is I3. So that based on the data was applied at this marks, it should be transferred to the output side. So this is about universal shift register. I hope you understand this. Thank you for patient listening.